Pistorius. Brown's trying to go with him. Peacock's in front. Pistorius starting to recover. It's going to be Peacock. Peacock takes the gold for Great Britain. Richard Brown takes the silver for the United States.
The field of prosthetics has existed for centuries. Archaeological evidence has shown that civilizations such as the Egyptians, the Greeks, and the Romans came up with their own replacements for lost limbs. The first prosthetic limbs were made out of wood, metal, or leather, which remained the standard for many years. Later on, different materials such as foam, polyurethane, and polyethylene that were painted the color of the wearer's skin became the standard in the making of prosthetic limbs. While this provided a cosmetic solution, it did not allow the user to utilize the new limb and was uncomfortable, not durable, and prone to infection. With recent advances in computers and microprocessors, the field of prosthetics has gone through exponential growth. This has led to the rise of myoelectric prosthesis, prosthetic limbs that utilize electrodes to pick up electric signals from the residual muscle in the user, allowing him or her to control the prosthetic limb much more naturally. Users can now control the artificial limb and perform almost all the functions that they could have with the original limb, such as running and lifting objects. The next great technological challenge in the field of prosthetics is the challenge of performance. How can we take the performance of prosthetics to the next level and bring a degree of true sensation to the user? How can we help someone who has lost a limb, or perhaps was born without one, acquire a sense of feeling to the environment around them? The goal then is to create prosthetics that enable sensation, more explicitly, the sensation of elements such as pressure, temperature, and humidity. The challenge to that goal is a materials one. As a result, scientists are employing the material science triangle, invoking processing, structure, and properties of a material. Researchers have to find a material that is durable yet flexible enough to handle the everyday stresses and strains placed on the limb. It must also be able to sense pressure and temperature while also being a good conductor of electricity, allowing it to send feedback to the brain. One of the main research projects addressing this challenge of prosthetics is electronic skin, or e-skin. Electronic skin is a thin film composed out of silicon wafers and polymers that through the use of microprocessors and electrodes will be able to sense touch. The first developments in this technology were developed by DARPA, or the Defense Advanced Research Projects Agency.
E-skin is made out of polymers such as PET, polyethylene terephthalate, with an elastic semiconducting polymer which scientists call an EMCP, which stands for an elastic microstructured conducting polymer. The polymer PET was selected specifically for the outer and inner shell of the e-skin because it provides a strong yet flexible covering. PET gains its strength from the long fibers created by heating the chains, which causes the hydroxyl and carboxyl groups to combine. A high degree of polymerization gives the polymer its strength and durability, but if the molecular weight is too great, the polymer will become too stiff and more useful in plastic products. By pulling and drawing the chains out, they can be layered in a linear molecular shape, which makes the polymer even stronger and more resistant to tearing and deformation. The outer shell of the e-skin needs to protect the more actual sensing material sandwiched in between its layers, making PET the perfect choice. The interior of e-skin is made with the polymer polypyrrole, which is created from the polymerization of the monomer pyrrole. Pyrrole was not the first choice for scientists because it is originally very stiff, brittle, and not soluble in water. Not good qualities for a flexible skin. But pyrrole was never ruled out due to its high conductivity because of its comparatively low band gap of 1.3 to 2.32 electron volts after it is polymerized. Ironically, pyrrole was eventually chosen because of its insolubility in water. When pyrrole was added to water, instead of dissolving, micelles formed, which are balls of the material that get attracted to each other with a strong polar and negative head. To polymerize these micelles, the pyrrole is p-type doped with either chemically or electrochemically to create chains of conductive molecules, making polypyrrole. These conductive balls of polypyrrole are elastic and squishy, perfect for sensing when pressure is applied and making it possible to send electronic signals to the nerve endings of the human. By taking lines of the EMCP 0.5 mm and 1 mm thick and laying them in a triangular arrangement overlapped with each other, the sensitivity of the e-skin was able to surpass that of human skin. The e-skin transmits the signals to the human brain by turning the electronic impulses into feedback, which is transferred through surgically implanted electrodes into the nerve endings and up into the human brain. E-skin is not nearly a perfect solution though, facing many problems that engineers and scientists alike are trying to find answers to. One of the problems that was faced when selecting the right material was the thermal conductivity and expansion of the materials. Most polymers tried had a thermal expansion point that was too high, meaning that the bonds would spread out too much when heated, either spreading out the band gap so there wouldn't be enough energy for the electrons to overcome the Fermi energy, or because of the expansion of the bonds and vibration of the atoms, interference with receptive parts of the E-skin occurred, creating false positives. This is the same for being cold, just opposite. This meant that when used in everyday life and climate, the prosthetic would be sending back sensations of pressure when nothing would even be going on. The transfer of the sensations of pressure in the skin to the human brain also needs more research. Electrodes have to be surgically implanted into the human, a costly operation and one in which the safety implications are not known. This problem is shown in the story of Abba Sorensen, who was one of the first humans to test a sensing prosthetic. He had electrodes implanted in his arm, tested a sensation prosthetic, and then a week later had to have the electrodes removed for unspecified health reasons. All of this research is expensive, and surgically implanting electrodes into humans isn't cheap either, making the idea of these prosthetic limbs out of the price range of most of the world's population. The synthesis and implementation of the E-skin will have to be cheaper in order to become useful in everyday life.
Why is all this significant? First, advancement in the field of prosthetics is crucial. Prosthetic limbs greatly improve the quality and ease of life for people who have lost limbs. Actions that were once out of the question for amputees are now commonplace, such as being able to partake in sports or lifting and grasping objects. Second, by adding sensation, as with the E-skin, amputees have in many ways acquired a real limb. This artificial limb will perform more like a real one, and by adding a sense of touch, it will help fill in what most amputees say is missing from their prosthetic limbs. Research has shown that by adding a sense of touch, amputees acquire a level of sensory detail to the point of picking stems off of fruit. Additionally, by receiving sensory feedback from the outside world, amputees no longer need to watch their prosthetic limb to see where it is. They can just depend on their sense of touch. The combination of all those factors will give amputees a limb that they can view as one that actually belongs to them and that isn't any less than a real limb. Why is this of interest to us? As future engineers, it is essential to understand how components of our lives, as well as those around us, are made and how they can be improved. Javin, a future biomedical engineer, has great interest in the field of prosthetics and how they can be improved upon. Brendan, a future mechanical engineer, is interested in the field of biomechanics and the actual construction of prosthetics and the materials that go into that. Khaled, a future systems engineer, is interested in the future of prosthetics and how by adding and analyzing sensory data, prosthetics can significantly be improved to bring amputees closer and closer to true sensation.